Welcome to the Deep Dive, where we unpack the latest research and pull out those key insights just for you. Today, we're diving deep into something core to modern AI, transformer models.
Yeah, they're absolutely everywhere, aren't they? Powering chatbots, image generation, you name it.
Exactly. But, even these incredibly powerful models have a kind of Achilles heel. It's their attention mechanism.
Mm.
Super powerful, yes, but the computational cost, it just explodes as the input gets longer.
It really does. It's this thing called quadratic scaling. Think about it like this. Every word or token needs to figure out how important every other token is. So if you double the length of your text, you don't just double the work, you quadruple it, or worse.
Quadruple. Wow, that's a huge bottleneck.
Mm-hmm. It really limits how much information these things can chew on effectively.
Which is exactly why our mission today is to really get into sparse attention. We want to explore how making attention smarter, more selective, can change everything, how models learn, how fast they converge, how well they generalize.
And we're looking at some fascinating research here, a paper in Notes that really highlights some, well, groundbreaking innovations.
And what's exciting for us, and hopefully for you listening, is focusing on the academic innovations. It's not just about making things run faster, although that's great.
Right. It's about the why. Why do certain methods work so much better? We're digging into the theory, the surprising findings, especially around this approach called TOPK, or heavy hitter attention.
Yeah, I think understanding this stuff is like getting a shortcut to why some AI models just perform better. You see the theory click with the actual results. We're expecting some real aha moments today. So let's start with that core problem again. This quadratic complexity and standard full attention. Every token looks at every other token. Thorough, but like you said, computationally brutal for long sequences.
Totally. It becomes impractical very quickly. So naturally, researchers first tried to find workarounds. The initial thought was, okay, let's just impose some fixed patterns, predefined rules for who gets to attend to whom. These were called input-agnostic methods because the pattern was the same no matter what the actual words or data were.
Right, like windowed attention, where a token only looks at its immediate neighbors.
Exactly. Or block attention, where you divide the input into chunks and attention stays within the chunk.
And there are others too, right? Like skipping tokens or random connections.
Yeah, strided attention skips tokens at fixed intervals, and random attention just picks a few random tokens to connect to. And sometimes, to try and keep some sense of the bigger picture, they had special global tokens. These could see everything, and everything could see them. Sort of like hubs, often used with the other sparse methods.
Okay, so these sound like logical ways to cut down the computation. Did they work? What did the results show?
Well, that's where it gets interesting. And where the academic story starts, they aimed for efficiency, sure, but the empirical results, they were often a bit disappointing. Many of these methods either made the models learn slower, they converged slower than just using full attention, or they just weren't as expressive. They couldn't capture complex patterns as well.
Especially without those global tokens, maybe.
Definitely. On tasks that need long-range understanding, like parity or cycle navigation, the simpler block or banded methods really struggled. They just didn't learn effectively.
So a bit of a dead end, or at least not the complete solution. These fixed patterns weren't quite cutting it. It seems like we needed something more dynamic.
Exactly. And this is the real breakthrough we're focusing on today. Researchers realized the model itself needed to decide what's important moment by moment. This led to input-dependent sparsification.
Input-dependent, so the sparsity pattern changes based on the actual data.
Precisely. And the star player here is heavy hitter attention.
Yes.
Specifically the TOPK variant.
TOPK. So instead of a fixed rule like look at your neighbors, it's more like look at the tokens that seem most relevant right now based on our current calculation.
You got it. For each query, it dynamically finds the tokens with the highest attention scores, the heavy hitters, and only pays attention to them. The pattern adapts constantly.
That feels much more intelligent. Okay, so what did the research find? How does this actually perform?
The results are pretty striking. First big finding. TOPK attention leads to drastically faster ERM convergence.
ERM convergence. Okay, so that's how quickly the model learns to get the right answers on the training data.
Yeah.
Minimizing its errors.
Exactly. How fast it gets good at the task it's being trained on. And faster training is huge, right? Less compute time, faster experiments, faster progress.
Absolutely critical. So how much faster are we talking?
Significantly faster. The paper shows TOPK significantly speeds up ERM convergence. For instance, on a task called list stops, It's about processing sequences of operations, kind of like logic puzzles for the AI. TOPK hit 95% training accuracy in 121 epochs.
Okay. And full attention.
Full attention needed 167 epochs. So TOPK was about 1.37 times faster there.
Wow, that's a solid speed up.
And it gets even more dramatic. On another task, even pairs, which involves spotting numerical patterns, TOPK was 8.83 times faster. It hit 95% accuracy in just 6 epochs.
6 epochs compared to
53 for full attention.
That's a massive difference, 8.8 times faster.
It is. And this consistent faster training, measured by the number of optimization steps, is actually a key novelty highlighted by the research. They state it's not something discussed in existing literature to the best of our knowledge.
So this isn't just a known side effect, it's a newly emphasized major benefit of TOPK specifically.
Right. It really sets it apart from those older input-agnostic methods, which didn't show this consistent speed up and sometimes were even slower.
That feels like a really important academic insight. It's not just efficiency, it's changing the learning dynamics itself. Okay, faster training is amazing, but the big question is always about generalization rate. Does it learn too fast? Does it overfit the training data and then fail on new stuff?
That's the crucial question. And here's the second really impressive empirical finding. TOPK attention also generalizes faster during training.
Faster generalization. So it gets better at handling unseen data more quickly, too.
Yes. And critically, this faster learning doesn't seem to lead to overfitting.
Okay, that's huge. So it's faster and robust.
Exactly. The study found TOPK achieves similar or better holdout accuracy. That's accuracy on unseen data, compared to full attention on tasks like even pairs, missing duplicates, and list stops. So you get the speed benefit without sacrificing and maybe even improving how well the model performs in the real world. That's incredibly desirable.
Definitely the goal. Faster training that doesn't overfit. That's a win-win. So the empirical results are strong, but why? What's the deeper reason TOPK works so well? This gets into the more academic, theoretical side, right?
It does. And the theory here is really elegant. It connects to concepts like Lipschitz continuity and semantic dispersion.
Lipschitz continuity. Sounds technical. What's the intuition there?
Think of it as a measure of smoothness. A smaller Lipschitz constant basically means the model's loss landscape, the sort of terrain it's navigating to find the best solution, is smoother, less bumpy.
Okay, smoother landscape. Easier to find the bottom, the best answer.
Exactly. It makes the optimization process much more stable and reliable, less likely to get stuck in bad spots. It gives stronger guarantees about convergence.
And how does semantic dispersion fit in?
Right, so semantic dispersion looks at the range of the scores before they get turned into attention probabilities by the softmax function. The key insight is that a larger range, a wider dispersion of these scores, actually makes the softmax operation less stable with respect to its inputs.
So if the scores are all over the place, the model gets less stable.
Pretty much. It's harder for it to make precise judgments when the input signals are wildly spread out.
Got it. So how does TOPK help with that dispersion? By picking the top scores.
Precisely. That's the academic innovation. By focusing only on the highest scoring heavy hitters, TOPK naturally narrows that range. It throws away the low scores that would widen the dispersion. So it significantly improves this dispersion, making the whole attention calculation much more stable.
Ah, okay. So it's not just sparse. It's sparse in a way that inherently stabilizes the math.
Exactly. And there's another related concept, semantic separation. This is the gap between those top scores that TOPK keeps and the lower scores it ignores. The research shows that having this smaller dispersion, which they denote collator for heavy hitter versus for standard, and even a decent semantic separation, leads directly to improvements in those stability constants we talked about.
Which brings us back to
An improved Lipschitz constant, which means stronger theoretical guarantees for convergence and generalization.
wow. It all connects. The faster training, the better generalization. It's theoretically grounded in these concepts of smoother landscapes and more stable calculations because of how TOPK selects attention scores.
Yes, and the empirical results, seeing those better Lipschitz constants in practice for TOPK, really validates the theory. It's a nice closed loop.
But that theoretical backing is really compelling. But, hearing about smoother landscapes is one thing. Can we actually see this difference? Did the researchers visualize it?
They did, using techniques to visualize the lost landscapes. It's kind of like creating a topographic map of the model's performance around the point where it finished training. Low spots are good, high spots are bad.
Cool. So what does the map look like for standard full attention?
Often the contours on those maps for full attention look somewhat asymmetric. especially near the center, near the solution. Think maybe lumpy, uneven valleys.
Asymmetric, so harder to navigate. Makes sense.
Yeah, it suggests a trickier path for the optimizer. It might be easier to get stuck or slowed down.
And for TOPK, what does its landscape map look like?
Much nicer. The loss surfaces for TOPK are described as quite symmetric, especially around that central optimal point. Picture a smooth, well-defined bowl or crater.
Ah, a nice symmetric bowl. That sounds much easier to roll down into the bottom.
Exactly. It visually represents a more favorable landscape for optimization. It directly supports why we see faster convergence. The path to the best solution is just clearer and smoother.
And I guess that stability also relates to the better generalization. Less chance of rolling off into some weird area.
Precisely. The smoother, more stable landscape helps explain both faster training and better generalization. And empirically, they found TOPK gives a smaller Lipschitz constant estimate, even when you move away from the optimal point, showing that stability holds across a wider area. The visuals really drive home the theoretical benefits.
What a fascinating journey from the basic problem of quadratic scaling to these really elegant theoretical and empirical solutions. We've really seen that just making attention sparse isn't the whole story. How you make it sparse is crucial.
Input-dependent, heavy-hitter attention like TOPK isn't just an efficiency hack.
No, it seems like a genuine innovation. Faster training, better generalization, more stability, and this smoother, more symmetric learning landscape. It's quite profound.
It really is. It's backed by solid theory, Lipschitz bounds, semantic dispersion, separation. It shows how digging into those fundamentals can lead to real practical advances.
It definitely makes you think. If efficiency gains through smarter algorithms can actually improve core learning properties like stability and generalization, what does that mean for the future?
Right. Could we use these principles to build even bigger, more capable AI models, but keep them stable and efficient enough to run on, accessible hardware?
And what new questions does this open up about the actual shape of learning landscapes for different problems and how we can design algorithms to navigate them better, not just faster, but more reliably?
Lots to think about. It feels like we're still uncovering some really fundamental principles about how these massive networks actually learn.
Absolutely. A lot more deep dives ahead, I think.